So there. Good day, everyone. Welcome to ME154. This is the second lecture of friction elements, and I am not sure if we will survive having this continuing to be online because the friction elements tend to get harder, or rather, I try to arrange it such that the easier types of breaks appear earlier. And then as we move along, it's going to get a little tougher. So unfortunately, we'll have to see with how well you do with the Xer. So for now, we'll be discussing just two types of new brakes that you will see in the industry. And these are the band brakes and the external shoe brakes. So let's get to it. So we're going to go to band brakes first. I think this is the one of the easier breaks to imagine. So basically, you just have any kind of flexible material like rubber or leather or braided rope, and you just loop it around a disc or a pulley or a sheave, and that brake, or rather that band, because it's being pressed against the wheel or the disc, it's exerting some frictional torque, which either controls the speed of the shaft that is connected to the disc, or it's causing the disc to lose speed. So it's kind of a simple thing to think about. Some of examples that you might not think of that exist. There used to be band brake bicycle brakes. I'm not sure if this is common still for the Dutch bike, but for most of the bicycles that I see, usually they're disc or caliper brakes at this point. You don't, I don't really see these kinds of band brakes anymore. These would be coupled to the rear wheel, if I believe. So maybe Dutch bikes still have these. Another vehicle that has band brakes are go-karts. So this one is, I think, custom made. So they might not be as common as I allude them to be. And here on the bottom left is an industrial brake. So there's this kind of stiff but still flexible band with some friction lining here. And there is some linkages here that will connect to some motor or some hydraulic ram that will engage the band here to cause the friction. So another kind of application of band brake is for dynamometers. In dynamometers, what you want is a measure of torque and speed. So for this case, in this middle example, this kind of resembles the band brake for the Pelton wheel and the Francis wheel in the Amped garage. If you've actually seen these in ME174.1, uh, this is kind of it. There's a here is a Newton scale, so it kind of looks a little different from what's in the Pelton wheel dynamometer, and then on the opposite side there is a measured weight. So instead of having two torque sensors or spring gauges, you just have one spring gauge and then one measured weight here. So it's kind of a very similar effect. It still has that. And here is to the left is kind of a very strange Pronibrick dynamometer. So you see here, there's this long flexible band. The dynamometer is actually here. It's in underneath this kind of makeshift roof, and the engine shaft of the tractor is here, and the band is actually making a cross. It's a cross drive. So this is kind of like one of those rare moments where you have these kinds of belt drives still. So I think you've seen this in ME45. I hope so. I hope you still remember this from ME45. This is a cross drive, and the engine drives the band drives this wheel, and this wheel is connected to a dynamometer. And it reads the torque and the speed that is produced by the tractor. All right, let's look at the band itself. We'll look at an element of the band here. So this is a section of the band, and the force acting on this element of the band looks a little complicated. So let's break it down. Right now, we're going to assume that the drum is rotating clockwise. So if it's rotating clockwise, the band is feeling a clockwise, or in this case, rightwards frictional force. That frictional force arises from the normal force of the drum pressing on the band element here. So that the band element is opposing the normal force while it is also being stretched along this direction. So there is a pulling force P, and of course there is some difference. One of the forces will be stronger than the other. So we're representing that with differential force P. And of course, this elemental has a length r d theta, so this is an arc length. So now if we commit to small angular approximations, and we take the force balance within the horizontal and the vertical direction, we get these force summations. Now, what I want you to pay attention to is this vertical equation first. So if you look at this, it may seem a little hard, but you'll notice that some of these kind of fade away eventually. So dp here, we can actually ignore it for a while. So we will get the summation of force P or load P times d theta is equal to the differential of the normal force. Now, if we interact with the horizontal summation of forces, we eventually get this. We eventually get this. So the differential of the belt load is equal to the friction factor times the differential of the normal force. To get a proper relationship, we just have to substitute what we obtained from the vertical summation, and then, of course, rearrange the equation. So we have the differential of the load over the load itself is equal to the force times differential of the angle. So if you integrate this, you will get the familiar equation from, I believe, NSI 11. I think I think it's in NSI 11. So this is the logarithm of the two forces, P1 and P2, is equal to the friction factor times the contact angle phi. And of course, if you want to get the torque that the band is exerting on the disc, we simply take the difference between the two loads. So we are assuming here that P1 is the larger load. So P1 minus P2 times the radius of the disc itself, or the drum, or whichever you are causing to slow down or causing to have its speed controlled. So yeah, we just derived an old equation from NSA 11. So all right, we have these equations. What do they mean exactly? So we're going to go into this little graph. So we're going to assume in this graph that P2 is going to be kept the same, but we are going to increase the friction factor of the band or the belt material. So we have this graph, we have a normalized torque here, normalized torque, and then we have an increasing contact angle. So what you notice here is that regardless of the friction factor, if you increase the contact area, you can transmit much more torque, essentially. So the more of the belt that you can wrap around the drum, the higher that braking torque you can exert. And also, if you increase the friction factor, so you get a rougher material to contact your drum or your disc or your pulley, the more torque you can transfer to the drum or brake itself, right? Now, if we solve for the pressure distribution over the entire belt that's in contact with the drum, we get this expression. So this is band pressure, small p, is equal to load over B. So B here is the bandwidth, or the bandwidth or the break width. So how thick the rope or the band or the rubber is contacting with the belt. So that's the width times the radius of the drum. So this arises from the normal force, as you can see from the derivation. Now, there is something interesting about the band pressure. If we graph our band pressure, or rather the pressure over the maximum pressure in the band, and then we try to measure that pressure, the normalized pressure across an increasing contact area, you'll notice that the highest pressure, the actuating pressure P sub A, is not affected regardless of how long the contact area is, or rather how big the contact area is. So what's going to change instead is if you wrap more of the belt around the drum, the smallest load or the smallest pressure over the entire band will actually decrease. So if you have a very low friction band, low friction material, the pressure will actually decrease slower. So there will be a slower decrease. But if you increase the friction factor, there will be a higher pressure gradient between the largest pressure and then the smallest. So what you'd also notice here is that the highest pressure is right at the edge of the contact, and the lowest pressure will be experienced at edge of the other edge of the contact. So the highest pressure and the lowest pressure will be always found at the endpoints of the contacting dots. And this one, it looks like if you graph it. So this is the pressure distribution. So the pressure is smallest at the endpoint here, next to our small load P2, and our pressure will be highest right next to where the band is being stretched by P sub 1, the higher load. So right, those are interesting things to think about. There is nothing else too complicated to explore here. NCI 11 has already done a good job at establishing this. Hopefully, it has, because I am used to ES11 covering this, or at least ES12. I'm hoping that this was talked about. So now we're going to go to the more difficult type of break. And I was supposed to make an example for this. Unfortunately, I could not really make one or draft one because of something that I was preparing for a few days and did during Tuesday. I hope that even though I might be a little late with uploading an example for this one, I hope that you'd peruse the handouts because the handouts have some of the examples. This particular one, external shoe brake, has an extensive example in the juvenile handout. Shigley prioritizes the internal shoe brake, so this type doesn't have an example there, but juvenile has, and it has one that is quite detailed, and I hope you peruse it. So right, let's go with the external shoe brake. So first of all, right, so what's the difference between the band and the shoe brake? So with this shoe brake, instead of having just a flexible rope, now you have something solid that is pressing a particular friction pad on the surface of the drum or the brake. And the difference here is that unlike the annular, uh, the the actual brakes, the cone brakes, and the disc brakes, the friction material is being pressed on the side of the drum or on the side of the disc. So the band brake is also similar in that regard. So yeah. Now there are several applications to external shoe brakes. So you can use this for hoists and cranes. You can use this for train brakes, and you can also use this for other industrial applications. What I'm showing now is just another form of dynamometer. So this is a Prony brake dynamometer. It's basically two solid brake pads pressing on this disc, and you can control the amount of torque that is being exerted by changing the weight that is attached to this arm. So you can hook up an engine or a motor, and then you can apply a fixed amount of torque upon the engine or upon the shaft, and you can check what the speed would be in this case. So more examples. This configuration, I found that the industry likes to call these thruster drum brakes. Basically, they are still external shoe brakes. You have brakes on the outside pressing on the sides of a drum, or in this case, yeah, it is a drum. And you have this very complex linkage. This one and this one are kind of the same. There is a hydraulic ram hidden somewhere here. I'm not sure if it's here or here, but basically this ram, wherever it is, actuates this entire linkage. It causes the brake pads to press further or relax their pressing on the drum. So this is usually used at this point for hoists or cranes. I think it's because the hydraulic rams allow for a lot of braking torque to be exerted. Um, you don't see these anymore for light load applications. Uh, you do see them on trains, like for example here. This is an ancient example. So this one is using a shoe brake directly on the wheel of this carriage. I am not sure what the logic is here, but I think it served its purpose during its time. However, external shoe brakes kind of are applied for trains here in this configuration. So you have shoes here, and then you have shoes here on the bottom. Um, they're a bit crude, but they do their job. So there might be some instances wherein a band brake would be a terrible idea. Maybe a disc brake would not provide enough of a stopping power. I think if you do some deep analysis on this, you can find what applications external shoe brakes are pretty good at. But now we're going to go into the force analysis, and um, I'm going to I'm going to preface this. This is quite a bit of a detailed force analysis. If you look at Juvenal's example for the external shoe brake, there are a lot of parts. Um, this one we're going to work with Shigley's example, which is just basically the drum and the shoe. But let's start here first. And once you've finished this part of the lecture, that's the point where I suggest you look at the Juvenile's example for this, because this is a bit of a doozy. So we're going to start with the drum. So this is the rotating part, and then this is the shoe. Will all shoes look like this? No, they won't look. They won't all look like this. But Shigley likes to use shoe brakes that are kind of that have their hinges here. So you have a shoe brake that kind of opens and closes. So like it can open its quote unquote mouth to relax, and then if it wants to apply pressure, it's going to close over the drum, like so. So some important coordinates. We do have a reference line. So this is the center line, or rather the line that connects the centers of the drum and the shoe brake hinge. So this is the reference line. This is where we'll be measuring the contact angle, theta, in this case. So theta is relative to the drum center. So keep that in mind. Next, we'll be defining a center to hinge distance A. So center to hinge distance A. Next, I will talk about the drum. So for the drum, it is important to identify what direction the drum is rotating. So for this illustration, our drum is rotating clockwise. And again, we are defining a coordinate theta from the reference line that we just defined. And we're going to use that to basically measure angles on the drum. That's right. Next, we have the drum radius R. So we'll use R reservedly for that. And then we'll talk about the shoe. So the shoe is quite interesting because it is interacting with two different angular coordinates. So on one hand, it is interacting with the drum. So part of it, especially the frictional surface, is interacting with angle coordinate theta. So when we want to measure the contact area, it is usually defined using the drum angle theta. However, we do have to note that the shoe brake is also rotating. So the shoe brake has its own shoe angle phi. At this point, we can just label it phi. So there are two angular coordinates happening right now. And what we want to measure the shoe angle with is the location of the actuating force. So Shigley assumes that the hydraulic ram or whatever linkage it is that you're going to use to press the brake on the drum is going to be applied somewhere here. So will it always be applied here at the endpoint of this brake? Not really. It could be applied here in some mechanisms. It could be applied further out, like for example in the dynamometer that you just saw an example for. So this will be actuating force F. We just arbitrarily put it here, somewhere here. And the location, or rather the radial arm of this actuating force will be defined as letter C. So C is the distance from this hinge to the application of the force. And this C should be perpendicular to where this force will be applied. All right. So again, will this force be applied in this particular direction? Not always, but we will set it like this just for this example. So, all right, so that's the shoe, and then we have the shoe lining. So the shoe lining is here. It is actually, although it's attached to the shoe, its geometry is more connected to the drum. So we define its contact area as the difference between theta 1 and theta 2. Rather, theta 2 minus theta 1. That is the contact. Now, right, when it comes to forces and especially the shoe lining or the friction pads, we have to have some means of defining the relationship of the pressure as you travel along the lining. So what I'm meaning to say is we have to find a function for the pressure that the brake is experiencing. And this can be a bit more complicated. Here is Shigley's um, drawing for the deformation that the drum is experiencing and the brake is experiencing. So there are two coordinates here. We have drum angle theta and shoe angle phi. We're going to skip the details. I'm going to leave the connections to you now. But these are some of the distances that we have to keep in mind. Aside from A and R that we already defined, we have distance OA, which is the distance from the center to the hinge. We have B, the location of the rim. And of course, we have H, the hinge to location distance. So this is the distance of B from location A. Now, if you do the math, or the geometry rather, you will get that the deformation of the shoe itself, like the shoe itself, has this deformation relationship. So it's H delta phi is equal to 2 R delta phi times sine theta over 2. Now, another thing that is deforming is also the shoe rim. So this is why I'm saying, uh, although the shoe lining is connected to the shoe lining or the shoe rim is kind of behaving in sync with the drum. So it has this particular relationship. H delta phi cosine theta over 2 is equal to actually this entity. You can actually sub this expression and you will get this. So what is the relevance of this entire expression? What you'd actually get here, what you want to get here is that uh, delta, the deformation of the shoe rim, is proportional to sine theta. And if you want to go meta on the NSI 13 relationship, you'd relate pressure as proportional to the deformation of the shoe lining. So by having this kind of meta assumption, if you take delta over sine theta here, you can kind of sort of substitute P, the pressure for the delta. So instead you get this kind of general expression. You get brake pressure P over sine theta, which is also equal to the maximum pressure, the actuating pressure P sub A over actuating angle sine theta alpha, sine theta A. So this the max pressure, and theta A denotes the location of the max pressure. So if you rearrange this, you get a function of the pressure like so. Now, okay, so what's the relevance of this? So this is relevant in locating the maximum pressure on the brake. And this depends on how extensive your shoe lining is. So keep in mind that we defined a reference angle from the drum center to the shoe hinge. So 0 starts here, and if you move your angular coordinate theta counterclockwise, you'll get an increase in angle. So this entirely depends on theta. So if the coverage of your lining is less than 90 degrees, the peak will always be at the end of the break. So for example, if your lining does not reach this vertical line, then the maximum pressure will always be at the end of the brake lining. However, if your brake pads are extensive, like they reach beyond 90 degrees, then the highest pressure will be at theta at 90 degrees. So this is a consequence of this function specifically. So if your coverage is within only the first quarter, then your maximum pressure is at the end of your brake lining. But if it exceeds the first quarter, or rather it exceeds the 90-degree mark, then 90 degrees will have your highest pressure. All right. So substituting our relationship function of pressure to our differential of the normal force, we will get this function. All right. So now that we have a relationship between the pressure and the normal force, we can now solve for a few things. So, all right. So here, since we are talking about rotating things, we have to look at the moment that the drum is exerting on the shoe. So there are two moments actually. There's a friction moment. So for example here, so initially we assume that the drum is rotating clockwise. So the drum is kind of pulling on the, or rather screeching on the lining in this direction. So this lining, this first direction has this radial arm, r minus a cosine theta. And if you go all out on the derivation, so this is the integral of the differential of the frictional moment is equal to the force times the radius. So this friction dn times the radial arm. And if you go on to derive it, you'll get this function here. So aside from that, you also have a moment from the normal force. So this dn. And this dn has the radial arm a sine theta. And if you go ahead, derive that expression, you'll get this. So these are the moments that are being experienced by your shoe. These are all being exerted by the drum. So what's the relevance of this? Why get this? We are getting this so that we can calculate the amount of force that we need to exert on this end or wherever in order to counter these moments. So again, these are the moments being exerted by the drum on the shoe. Now we have to exert an equal, or rather the appropriate force on the shoe such that the shoe can stay on the drum and exert the torque that we want. So the actuating force, it has to balance these two moments. So right now, uh, the two moments here, they are all acting in the same direction. They're all clockwise from our diagram. So the actuating force has to actually fight against these two moments. So we define a force F and we define a location, radial location C. So at this point, we assume that the force is here and our radial location C is here to here. So since our radial location is here to here, we assume that the force will be applied perpendicular to this distance, all right, to make these things easier. So now doing so, we get this expression. This is now the expression for the actuating force. We get the frictional moment, we get the normal moment, and then we obtain the radial distance, and then we get the actuating force. Now, there is another discussion here. We have this label non-self-energizing. So if you look at the frictional force here, uh, or rather the frictional moment here, this moment wants to push the brake away. So it wants to push the brake away from the drum. So that is what we call non-self-energizing. None of the moments that the drum is exerting is keeping the shoe or the brake itself on the drum. So none of these for all of these forces want to push the brake away. So this is what we mean by non-self-energizing. You have to exert some level of force to keep the brake or the shoe on the drum. So all right, now that we have some means of calculating the force, we have to complete our we have to be comprehensive with our free body diagrams. So we calculated for the force. Now, to complete the free body diagram of the shoe, we also have to calculate for the reaction on the hinges or on the pin of our shoe. So this is our brake force. This is the reaction on the shoe lining, and we're going to assume that these are the positive directions of our hinge reactions. And I won't bore you with the details of deriving is. I think the diagram itself is sufficient enough to give you an idea on how to derive this. Basically, the reaction forces are this. So isn't this way too hard? It does get a bit tedious because you are solving for two moments and two reactions. So here's a bit of a shortcut. So we can assign coefficients A and B to these particular expressions because they do show up in the friction moment and the normal moment expressions. And if we do that, we arrive at these expressions. So what's going to happen here is that if we go back to our go back to our moment analysis, we can actually substitute these back. We can actually calculate for these in advance and then redefine the equation such that it's actually easier to handle. So when we're handling shoe brakes in general, it's nice to have a shortcut coefficients here. So what you do is just go for the shortcut coefficients first, solve for these, and then find where these expressions may be found. So for example, I did the legwork, or rather Shigley did the legwork and redefine the hinge reaction such that now they are like this, essentially. So using this, you essentially eliminated the integrals from the equation. So now it's just straight up substitution. So what about the friction, the force, the actuating force? I believe you can do the same for the friction moment and the normal moment. So just going to leave it up to you to solve. So now the torque on the drum is defined as the integral of the uh, friction force friction force times the radial arm, and that is this entity here. All right, so that is for the free body diagram analysis or the force analysis on a non-self-energizing drum. So what if we have a drum that is self-energizing? Like, what would that look like? So, okay. So for this example, I didn't change anything except the rotation of the drum. So before we were calculating for the drum that is rotating clockwise. So now I flip the direction. The drum is now rotating counterclockwise. So what you notice here is that the frictional force FDN is now in the opposite direction. So it's now acting in this direction. And what you get here is that at the shoe, it is now exerting a counterclockwise moment, while the normal force is still exerting a clockwise moment. So at this point, you have an opposition of moments that the drum is exerting. So here, when you have a self-energizing drum, the drum is actually helping the brake keep on the drum itself. So the force that you have to exert to keep the drum on, or rather keep the brake on the drum, is actually much less. So you have this difference between the moments instead of an additive. So it is a bit of a relief. And if you have a double shoe configuration, like for example here, you can have two shoes. One of them is non-self-energizing. So one of them will be exerting much more force. And then you have this other shoe that is having no trouble at all. It needs a lot less force to exert the torque that you need. And since this is a different kind of configuration, the hinge reactions will also be different. So these reaction forces here are applicable only to the self-energizing brake, and only if you assume that these are the positive directions of the reactions. Right? So if MF here is actually equal to the normal moment, you get this situation of what we call self-locking. So essentially, uh, the drum itself will do that exertion of the braking for you. So again, if these two moments equal one another, then you don't have to exert any force at all. So perhaps you can connect a mechanism here just to decouple the shoe, because the drum wants the shoe to be on there if MN and MF are equal. So that is when self-locking is engaged. So self-locking is a particular situation for a self-energizing brake. So not all so all self-locking brakes are self-energizing, but not all self-energizing brakes are self-locking. Right. So is there an example? Again, I already mentioned that we won't be having an example for this case because I did push a lot of my time towards that particular activity I was doing on Tuesday. So, right, let's talk about the shoe brakes themselves. So, there are some things that we have to note, especially if you're going to work with this in the industry. When suppliers give you particular values for the brake material, keep in mind that it's usually in averages. So when I mean averages, it might be that the brake material that you get might be weaker or stronger than what is actually uh, given in the catalog. So
you might need some statistical help there on that part. Also, we actually ignored the centrifugal forces that are acting in this thing. If you recall for ME45, when we have terrible acceleration, we will get centrifugal forces. However, so here's the thing, we can ignore it because our shoe is actually planted on the ground. So if all of our linkages are actually grounded, we don't have to think about the centrifugal force all that much. However, if this shoe is functioning as a clutch, so like for example, if you recall, a clutch is supposed to transfer rotation from one shaft to another. So if you're going to use a shoe configuration to transfer rotation from one into another, that's when you have to consider the centrifugal forces. So at this point, we don't have to because most of the um, popular applications of shoe friction elements is for braking. So unless you want to design a shoe clutch, fine, all right. So that's when you have to consider the centrifugal force because the mounting for the shoe will be rotating as well. So yeah. Next is the calculations or rather the derivations that we did assume that the shoe is rigid. So of course, we did assume that there will be some deformation to the shoe. But for the first analysis, we kind of glossed over that part. So technically, the pressure distribution may be different from the sine curve that we showed you. So uh, take it as kind of a conservative or at least a simplistic approach when you're trying to find for the maximum pressure. So the last one that we want to note is that the friction factor, at least in all of our analysis for friction elements, we assume to be constant at every point. So here's the thing. I think NC 13 did not discuss this, but for real friction pads, for real friction materials, their friction factor actually changes with the temperature. So if the friction pad gets too hot, you will get a fluctuation of friction factors. Also, when the band or the brake is wet, you tend to see a reduction in friction factor as well. And also, depending on the environment, you could get some funky things happening to your braking materials. Keep in mind if you're using um, a very hydrophilic braking material and you're using it in a very humid environment, you could get some wetness in the brakes. That could cause some reduction in the friction factor. But yeah, those are the things that you want to note for shoe brakes. So is the example coming? I'm actually not sure. Depends on how much energy I have left because I really expended a lot of energy for Tuesday. So let's see what we're gonna get. So yeah, that'll be all for now. So these are my references. Just these two, because I really did not have time to look at the other peripherals. So maybe next semester, I'll try. So until then, thank you so much and have a great day. Stay safe.